Hello, my name is Sarah Taji, and today I'll be talking about one of my favorite chapters in my discrete class, which is chapter 3. But mostly we're going to talk about chapter 3.1, which is propositions. Chapter 3, just to give a little background, talked about a lot about logical gates and what each logical gates mean. And chapter 3.1 talks about propositions like true and false statements. And as a computer science major, I really use true and false statements a lot in my codes. And that just made this journey really easy for me and more exciting because I just wanted to learn more about it and what it means in mathematics. So let's get into it. What are propositions? So, propositions in mathematics and logic is a statement that is either true or false. Propositions are typically used to convey information to make assertions about something. For example, 2 plus 2 is a proposition that is considered to be true, while 2 plus 2 equals 5 is a proposition that is considered to be false. Propositions are often used in logical arguments and can be combined with logical connectives such as and, or, and if, and etc. to form more of complex statements. In addition to being used in logical and mathematics, proposition is also used in computer science. So now we're going to split up proposition and talk about the different branches. So the first one is going to be logical disjunction. The definition of that is if P and Q, so let's just say P is 2 plus 4 and Q is 2 plus 2 equals 5 are propositions, then the disjunction is P. So when you see that symbol, which is P, which is between P and Q, that symbol means and. And the tables that you see below is called truth table. The table on the left has the table as T and F. T for true and F for false. And then it just shows how if P, which is true, and if Q, which has F, which is false, will have true. So the statement will always be true. So it has to have one of them as true for the statement to be true, as you can see. So we have true and false. On the second row, we have true and false, and it automatically has it as true. So no matter what, if one statement is true, the outcome will always be true. It has to be balanced, like false and false will always come out as false. But if it's true or false, it will always come out as true, no matter what position it is. Like even if it's false, true, it always comes out to true. And the second table that you see on the right, that one is in binary format, which 1 means true and 0 means false. It just has a layout like that. So that is logical disjunctions. The next one that we're going to talk about is logical conjunction. Logical conjunction, so is exactly what disjunction means, but instead of the symbol that looks like a V, it has that symbol that, as you can see, between P and Q. That symbol means or. So it's exactly like disjunction, but the opposite. So what that means is that, let's just say if the statement is true, if P is true and Q is true, it will be true. But if P is true and Q is false, it will be false. Both. So it's exactly like disjunction. So if the statement at least has one true, it'll always be true. But this one, conjunction, If there's a false, the statement will always be false. And on the left, as you can see, it is the binary format, which is 1 and 0, just like the previous slide that I showed you, 1 representing true and 0 representing false. And now let's get more into it, talk about more other logical gates. So we have logical negations. Negations they mean not. So whatever P is, now P is the opposite. So if P was true, P will be 1, right? So let's just say, as you can see the table right here, let me show you. So as we can see, as this table right here, P is 1 and 0. And if you have the symbol of negation next to P, it will become opposite of whatever P was. So now P, instead of being 1, it's 0, 1. So that's negation. And then we have conditional statements. And what conditional statements means that if P, then Q, denoted by this right here, as you can see. And they put it in a truth table, as you can see, is that means P is now Q, right? So you just switched positions. The next one that we have is exclusive or statements. So the symbol that you see here that has a plus in a circle, it's a or statement. And that is the truth table for it. So that's logical gates. And then the next one that we have is biconditional statements. A biconditional statement is saying like P if and only if Q. And it's denoted by that symbol, like two-sided arrow. And that's a truth table for it. So if P is 1, Q is 1, and now P if only if Q, it will give us this outcome, as you can see right here, 1, 0, 0, 1. And then we have, I added this because this gives out more of a visual understanding, because instead of using symbols, it uses words. So what we have here is there are several alternatives, wordings for conditional and biconditional statements, as you can see here. So if P, then Q, we could word it as P implies Q, or Q follows P, or P only if Q, and etc., as you can see. And then we also have P if and only if Q, and we could word it as you see here. And then for the next slide, I also added these 3 other definitions. So these are just like saying the opposite, the converse and inverses of the propositions. So for example, for inverses, proposition, so let's just say adding the negation into it. So it goes from this to this. It's just the opposites, and it's good to know about these as before I get into the examples that I'll be showing you and doing it with you guys. And yeah, so let's get into the example. All right, so let's get into an example. This is a question from problem set number 4. It says that let D equal to I like discrete structures, and C equals to I will pass this course, and S is equals to I will do my assignments. All right, and then for each statement, we have to put it as the proposition symbolic form. So for A, it says, I like discrete math and I will pass this class. So as we can see, there is a and. So, and in the question, we saw that I like discrete math is C and I will pass this course is C. Sorry. I like discrete structures is D and I will pass this course is C. And that's how we write the symbolic form of proposition. Because of this means and. And then the next one we have for B is that I will do my assignments or I will not pass this course. Again, we have a or. So now, as we remember, I also added this. And is that symbol, and or is that symbol, and not is that symbol. So now, we look at the statement. As you can see, it says, I will not pass this course. And from the question, we don't have that statement. So when we look at C, because C is the closest one to it, it says, I will pass this course. And if you want to add a not, we add the negation, which is this symbol right here. So that will equal to this answer right here. And then for C, it says, it is not true that I both like discrete structures and will do my assignments. So this is kind of tricky. I got confused in the beginning too. We have to focus on this not right here. This not is already saying that every statement following after this not is going to be false. And what did we say would make the statement not true? Is negation. So we have to put a negation before we write out the statement. So we take it apart. So what we see is that I both like the structure math. So the structure math, discrete math is D, as we can see here. And then we'll do my assignments. Is S. So it's gonna and S, right? And how do we say the statement is not true? By adding a negation. So it will say not this and not this. And then the last one we have, for D, we have I will not do my assignments and I will not pass this course. So it's going to have two negations before each of the statements because it has one here and it has one here. And it also has and. Yep, that's for number one. And I also have these, but let's not get into it, but I will upload it in my website. Thank you for watching.